Welcome to the course on computer design of electrical machines. We will have a lecture 35 today on design of stepper motor, stepper machines part 2. So, with the outline of presentation, we will like to consider today design consideration and specification, the determination of design parameters like stator, rotor and winding parameters, performance calculation, design workflow, finite element design of stepper machine, exercise and numerical problem followed by references. Coming to design consideration of stepper motors. Stepper motors are widely used in various applications including robotics, CNC machines, 3D printer and many more. And when designing a system that incorporates stepper motor, several important considerations will be taken into account to ensure optimal performance and reliability. And here are the some key design considerations for stepper motor. Typically, the stepper motor type. So, choose the appropriate stepper motor type based on the application requirement. Then common type of stepper motors like permanent stepper motors suitable for low and moderate performance analysis. Then variable reluctance step motor typically used in high speed and low torque application. Then hybrid stepper motors, a combination of PM and variable reluctance stepper motor providing a balance between the performance and cost. Now, the second is the step resolution. So, determine the step resolution required for application, and higher step resolution provide smoother motion but may require more complex control electronics. And third is the driver selection. So, choose a suitable stepper motor driver that matches the motor specification and the overall system performance, and consider factors such as micro stepping capability, current rating, voltage capability and communication interface like pulse public direction or SPI. Now, coming to power supply, ensure the power supply voltage and current are within the specified range of stepper motor and the driver. Using an appropriate power supply is the crucial for reliable and efficient motor operation with the stability point of view. Fifth is the heat dissipation. The stepper motors can generate heat during operation easily at high speed or under heavy load. To implement a cooling system or select a motor with sufficient thermal characteristic to prevent overheating. Now, sixth is the load characteristic. To consider the mechanical load the stepper motor will drive, ensure that the motor torque and speed specification match the requirement of the application. Then seventh, acceleration and deceleration. The design the motion profile with the appropriate acceleration and deceleration ramp to prevent sudden change in velocity, reducing stress on the motor drive and improving the overall stability. Then eighth is the environmental condition. To evaluate the environmental condition when the stepper motor will operate, and factors such as temperature, humidity and dust can affect the motor performance and longevity. Ninth is the feedback system. So, depending on the application, consider integrating feedback systems such as the encoder or sensors to provide closed loop control and to improve accuracy, especially in high precision application. 10th, micro stepping. If smooth motion and reduced vibration are critical, consider using micro stepping, and micro stepping allow for finer resolution and can help to minimize resonance effect, but it may require more advanced stepper motor control driver. 11th is the system integration. To ensure that the stepper motor is seamlessly integrated into the overall system design, and consider factors such as wiring, connectors and control interface. So, now coming to design specification of stepper motors. So, coming to design specification of stepper motor covers various parameters that define their characteristic and performance like step angle, step accuracy, holding torque, maximum operating speed, rated torque, resistance and inductance, deterrent torque, number of phases, voltage and backlash. Then in driver configuration, whether required is bipolar, unipolar or chopper. And then the rotor inertia, physical size, shaft configuration, ambient temperature, insulation class and vibration noise. Now coming to design equation. So the size of the motor from the torque requirement is as follows: T equal to K dr square into LSK, where T is the torque, K is the output coefficient, proportional to the product of electric and magnetic loading, typically of 0.65, and for stepper motor less than 4.0 in outer diameter rough gauge initially, and dr rotor OD and LSK rotor stack length. See the cross section in the next slide. All these dimensions are mentioned here. Typically the motor is structured with various design parameters, as LSK is the stack length and the remaining, you can just see the DS is the outer diameter, then the rotor diameter is dr, and of course the separate dimension like pole arc and pole pitch and the different dimensions otherwise. So size and rotor from the inertia requirement. The rotor assembly consists of a shaft and rotor body with salient poles on its periphery. Since the shaft and rotor body all rotate about the same axis, the inertia J for each part may be calculated separately. Then they may be added together to get the total inertia as JRS equal to J rotor plus J shaft. There JRS is the typically inertia of the rotor and shaft assembly, including the load. And this is typically like a side view of the motor structure with various design parameter, as you can say LSA, the shaft and the distance between typically your bearing to bearing, and the rotor shaft and shaft dimensions and total length of the typically of the shaft. Apart from that, the you can say cross sectional wise, typically what is the you can call it the complete diameter of the rotor like dr, then the poles dimensions and the shaft dimension d shaft, and then typically the radius of typically at the maximum pole arc as well as the minimum pole arc. So now again the JRS equal to J rotor per J shaft, where JRS is the inertia of the rotor and shaft assembly, where J shaft is equal to 0.0184, D shaft is by 2 power 4 into L shaft, and J rotor is J poles plus J cylinder, and that J cylinder is 0.0184 dr minus 2 drs by 2 to power 4 into LSK minus 0.0184 D shaft by 2 to power 4 LSK, and the J pole equal to J ring into WT poles divided by WT ring, and J ring is equal to 0.184 dr square dr upon 2 power 4 LSK minus 0.0184 dr minus 2 drs by 2 to power 4 LSK, the WT ring equal to pi RR square minus RR minus DSR square into pi into LSK into rho steel, and WT poles is DRS WRT LSTK into NR into rho steel, that is the density of the steel, and here WT ring and WT poles are the weight of the ring and poles respectively, and rho is the density of the steel material. Now since the shaft is known, calculate its inertia first and subtract it from the total allowable inertia, and then select the largest rotor diameter, and that is practically for the allowable motor diameter and length. The larger the diameter, the more torque available per unit length, and try to measure the load inertia as reflected to the motor. At this point in the design, one have not selected the DRS dimensions, that is depth of rotor slot, and so the estimate it as a 30% of RR. And now the DRS is known, save the rest of the allowable motor diameters of the stator, and now note here the stator diameter OD should be normally greater than 2 dr, and dr is the stator bore diameter. Now all the major dimensions required to produce the torque are known except the air gap length. Now sizing the air gap length of variable reluctance stepper motor should be kept between 0.12 mm to 0.5 mm per side, and this requires very tight matching tolerances. Now coming to typically selecting the number of phases and poles. So typically, you require, if you have a 3-phase, always has a positive torque, high torque ripple, and poor torque ripple to have average torque ratio, and low number of power transistor like 3 mm. In 4-phase, the low torque ripple but good peak torque to average torque ratio. In 5-phase, lower torque ripple and more expensive controller. So now coming to selection of the phases. So this is usually a requirement of the drive system to be used. However, some people prefer a 3-phase motor because it utilizes the largest percentage of the iron and copper at a given time, while the others prefer 4 or more phases because of the reduced torque ripple and slewing operation. It is now necessary to select the number of stator and rotor teeth required to achieve the desired step angle. So the step angle is defined as the difference in the stator and rotor tooth pitch expressed in degrees. Example is 12 stator teeth and 8 rotor teeth. So step angle is 360 by 8 minus 360 by 12. So it's a 45 minus 30 degree equal to 15 degree. So number of rotor teeth must differ from the number of stator teeth by number of poles. It is generally desirable to have free rotor teeth than the stator teeth because free rotor teeth yield low inertia and flux per pole, and consequently the torque is a function of tooth pitch of the member having the largest number of the teeth, and the number of poles should be made as large as possible because of the torque vary directly with the number of poles. Another combinations are possible and may prove to be better choice for a given application. And some consideration when selecting the pole combination are following. Selecting the higher number of stator pole leads to more winding, a smaller step angle, and more flexible, more expensive controller, and higher core loss for a given shaft speed. And now coming to stepping rate. Stepping rate is equal to 0.539 under root TS 386 by JT, where TS is a shaft torque in inch and JT is the motor plus load inertia, that is 1 inch and second square. And step angle, your SR equal to SS plus minus B and SS equal to MPN. So theta S equal to 360 upon SS minus 360 upon SR into N, where M is the number of phases, P is the number of poles per phase, and SS is number of stator slot in at the air gap. SR is the number of rotor slots, and theta H is the step angle in degrees, and N is the number of smallest teeth in one tooth pitch of each major stator tooth SSM, and where the N is greater than 1, where small n is greater than 1, SSM is equal to MP. And now typically step angle for different motor structure, typically 2-pole 3-phase step angle theta, when P equal to 2, M equal to 3, and SM equal to 6. So you have a, with the S going vary 1 to 6 and SS have a combination, these are the step angle from starting from 30 degree to 1.935. Similarly for 2-pole 4-phase motor, step angle, the pole equal to 2, M equal to 4 and 4 phase, and SM equal to 8, and then for N varying 1 to 10. So you have again typically step angle go to varying from 15 degree to 1.0976 degree. So now coming to 4-pole 3-phase step angle. Again here P equal to 4, M equal to 3, and SSM equal to 12. So here again you go to typically a N equal to 1 to 8. So step angle goes from 15 degree to 1.2 degree. Similarly for 4-pole 4-phase, so P equal to 4, M4, and SSM 2. So keeping N equal to 1 to 8, you get the step angle starting from 7.5 degree to 0.6818. Similarly 6-pole 3-phase step angle, P equal to 6, M equal to 3, and SM equal to 118. So if N goes typically 1 to 6, then you go theta equal to 10 degree to 1.056 degree. And for 6-pole 4-phase step angle, P is equal to 6, M equal to 4, and SM equal to 24. So varying N equal to 6, so you get the step angle 5 degree to 0.600 degree. Now coming to typically lamination design. After selecting the phases, pole, and teeth required for the motor, it is necessary to complete the stator and rotor laminations design. So for stators with the 1 tooth per pole, use the following method for the determining sizes, except be certain to leave gap between the poles and the stator inner and diameter and large enough to insert the winding. And if a needle winder is being used, this may be determined as follows. So width of the stator inner diameter, WSO equal to maximum wire OD plus 0.010 inch, clearance width for maximum wire plus 0.025 in needle wall, and 0.010 in clearance for needle movement, and plus 2 into slot insulation thickness. Now sizing the pole. So generally the steel width throughout the magnetic current should be about equal to the yield the same flux density, and the stator yoke width WSI, if you look into the figure, may be little larger to reduce the MF drop in that region, since it is such a long flux path. So for the stator section, the pole arc theta SP of the figure and the gap between the poles should be about equal. Therefore theta SP equal to 360 by 2 NS. Now typically sizing the pole side should be parallel each other from the stator board to the intersection with the stator yoke, and this leaves a large trapezoidal area for winding space between the poles. And the stator yoke with width WSI should be equal to or greater than 1/2 of the pole pitch. And if in VR stepper motor, it is common to make WSI equal to WST, and the rotor pole arc theta RP should be equal to the stator pole arc. Now sizing the pole, then the rotor pole width WRT should be made equal to the stator pole tooth width, and the depth of the rotor tooth width should be at least 220 times the gap length, and rotor pole yoke width WRY should not be less than half of the rotor pole width, that is WRY greater than 0.5 WRT. Now estimating the slot area and winding space for the straight sided teeth. So before a winding can be calculated, it is necessary to determine the available slot area. First, calculate the gross slot area, that is GSA, then subtract the insulation area, the winding needle area, and the slot wedge area. As you can see in the diagram, so DSS equal to DS capital D small s minus DR minus 2 in bracket LG plus WSY by 2, where DSS is the stator slot depth, DS capital DSS is the stator outer diameter, DR is the rotor diameter, LG is the air gap length, and WSY is the stator back iron length. Now calculate the GSA by calculating the total area of the motor inside the stator yoke AS1 and subtracting the area occupied by the rotor and the air gap AS2. Then divide by the number of slots NS, and finally subtract the area of the pole AT1. So GSA equal to in bracket AS1 minus AS2 divided by NS minus AT1. Now where AS1 is pi RSS square and RSY equal to DS minus 2 WSY by 2, and AS2 equal to pi in bracket RR plus LG square, and AT1 in bracket RSS minus in bracket RR plus LG bracket close into WST. So here AS1 is the area of the motor inside the stator yoke, and AS2 is the area occupied by the rotor and the air gap, and LG is the air gap length, and WSY is the stator back iron length, as you can see in the dimension. So to find out the net slot area NSA, subtract the area occupied by the insulation AINS and the area needed for the winding needle ANED and the area needed for the slot wedge AWG. So ANED equal to in bracket DSS minus 2 TNS into WNED, where WNED is the width of the winding needle including the clearance, and TNS is the thickness of the slot insulator. So the area of the insulator takes up the slot ANS in found edge. NS equal to in bracket 2 DSS plus WSS2 in bracket TNS, and where WSS is the arc length of one slot inside the stator yoke, and the given edge WSS2 equal to RSS into theta h, and theta is equal to 2 pi upon NS minus theta SP. Now area of the wedge AW wedge is equal to W wedge into T wedge, and new slot area equal to NS equal to GS minus in bracket ANED plus AN plus A wedge. And to find out the slot area available for winding per pole, divide NSA by 2. So AWP equal to NSA by 2. Now coming to number of turns per pole. So number of turns per pole NP can be estimated by determining the ampere turns required to nearly saturate the steel chosen for the motor laminations, then selecting the wire size. Then that will keep the current density reasonable, and stack length may have to be adjusted. The actual winding section is heavily dependent on the drive type, and once the number of turns has been calculated, that can determine the wire size that can be used. So once the wire gauge is calculated, then the RPH resistance per phase is calculated. Divide this value into Vs to determine the maximum current possible. So AWP equal to NP ODW square, and ODW is under root AWP upon NP, and I max equal to Vs upon R phase. So to determine the resistance, the mean turn length and number of turns and the gauge of wire known, MELT equal to 2 in bracket WST plus 2 RRC, as you can see in the dimensions. So where MELT is the mean and turn length of the pole include the both ends, SRC is the mean length of the turn at the coil corner, and WST is the width of the stator teeth. So now here SRC equal to RC into theta RC, and theta RC equal to pi by 2 equal to 1.57 radian, and mean turn length per pole is MTL equal to METL plus 2 into LST, okay, and resistance per pole is RP equal to NP into MTL into rho upon AC. As you can see in the dimensions, the resistance per pole RPH equal to RP into number of poles divided by number of phases, and slot fill factor is the ratio of the conductor area over the total slot area. So slot fill factor equal to NP into area of single conductor divided by slot area, and estimating the radial torque, so TPK equal to 0.1129 into 10 power minus 5 P into P by 2 in bracket dr by 2 plus LG by 2 upon LG into LSTK into NP upon P 2 square into I square in odd inch, where P is the number of pole and I is the current in per phase. Now acceptance range of stepper motor parameter for 1.8 degree PM stepper motor, the rotor teeth is NR50, and number of stator pulses 8 and number of rotor pulses 5. So stator tooth width to tooth pitch equal to 0.9 034 to 0.6, and tooth pitch upon air gap is 10 to 200, and total height to tooth pitch 0.4 to 0.6, and pole pitch width to pole length is 0.30 to 0.60. Now, your acceptance edge for stepper rotor per magnet, OD upon rotor OD equal to 0.5 to 0.8, and ID upon OD equal to 0.5 to 0.75, length of oblique rotor stack length 0.3 to 0.6, and flux density in stator and rotor teeth 1.2 1.5 Tesla, and B pole to B teeth 0.75 to 0.9, and B yoke to B pole equal to 0.75 to 0.9. Now, typical leakage flux between the poles to total pole flux 0.04 to 0.06, and solid stack length to a hollow shaft length 0.95 to 1, and MF provided by the rotor palm magnet equal to 2 into MF due to energization of stator winding. Now coming to performance calculation, and an FEM design using finite element analysis software results are compared with the result of empirical formula based result for the design validation, and certain empirical formula are developed for the motor key performance calculation, and the motor performance are mainly back EMF, cogging torque or deterrent torque, and static torque and single phase and multi-phase excitation. So now typically the static torque with the single phase excitation is given as TS1 equal to NR up by 2 in bracket NI into PM into FM into rho 1 upon rho 0 and sin theta I plus delta I T, where NI is the ampere turns provided by energized stator winding, PM is the permeance of rotor palm magnet, and FM is the MF produced by the rotor palm magnet, and rho 0 and rho 1 equal to coefficient of Fourier series expansion of air gap permeance, and theta is the rotor displacement from fully aligned position in degree, and delta T equal to torque due to the higher order harmonic. Now the static torque with two phase excitation is given as TS2 equal to root 2 into TS1 into sin theta I plus 45 plus theta delta T, where TS1 is equal to static torque with single phase excitation, TS2 is the static torque with the two phase excitation, and deterrent or cogging torque T cog equal to minus N up by 2 PM FM square in bracket rho 4 upon rho 0 equals square into sin 4 theta I, where rho 4 is the coefficient of fourth order harmonic component of air gap permeance. Now coming to palm magnet performance and MF, the palm magnet performance and MF are given as PM equal to mu M AM upon LM, and FM equal to FBD LM by BM, where AM LM are the area of cross section and length of the rotor palm magnet, and BD is the operating point of flux density on the demagnetization curve of the palm magnet huge, and mu M is the permeability of the palm magnet material, mu R is the relative permeability, and mu 0 is the permeability of free space. Now coming to design workflow of the stepper motor design. So there are two phases in the design procedure. Phase 1, the starting point of the design consists of the step of specification of the motor, step angle, static torque, number of the phases, length of air gap in millimeter, and rated current in ampere, and the specification of the material to be used, that is palm magnet, soft magnet material, class of insulation, etc. also to be needed to define. Now coming to phase 1, the overall dimensions such as diameter in millimeter and stack length LSK are sometimes specified with a view of to conforming with the standard practices and constraint imposed by the application, and the design procedure computes stator pole and the yoke dimensions, rotor disc dimensions, rotor palm magnet dimensions, and stator and teeth, rotor teeth and slot dimensions, as well as the air gap. Now phase 2, this phase consists of design verification. So in this phase, detailed magnetic circuit computation are performed with the view to ensuring that the flux density, especially in the teeth, are within the limit imposed by the material is selected, and these computations also yield that ampere turns required, and this enables the design of the phase winding to be carried out. Now phase 2, thereafter the motor static torque and deterrent torque as well as the phase winding resistance and inductance are computed, and the moment of inertia is calculated in figure of made such as acceleration T upon J, power rate and torque to power ratio are also computed to ensure the motor design is satisfactory. Finally, temperaturized calculation is performed to ensure that the temperature is within the permissible limit. And this is the typically flow chart of stator motor design, starting from input motor specification, step angle, holding torque, number of phases, phase sequence, bifilar or unipolar or air gap, KST and lead. Space the palm soft magnet wire, winding wire, insulation material. Then read the material data file, read design parameter range file, then select the design parameter, then design the return rotor disk, then design the PM on the rotor, compute the flux density ampere turns in all parts, and then check flux density within the limit. If no, go back to again to adjust the design of stator and rotor disk. If yes, design to stator winding, then compute holding and cogging torque, resistance, inductance, and rotor inertia. Then check figure formality, it is okay. If no, then go back to again to adjust the design dimension, and if yes, compute the temperature rise if temperature within the limit. If no, go again back to change the dimension. If yes, print the result and stop. Now coming to finite element analysis of the stepper motor. Finite element analysis is a powerful tool in the design and analysis of stepper motor. The finite element analysis can provide accurate electromagnetic analysis results and detailed magnetic field distribution of electric machines with considering excitation, advanced material property, losses, and demagnetization. Now, some of the steps involved in finite element design of a stepper motor: geometry and matching, metal properties, electromagnetic analysis, static and dynamic structure analysis, thermal analysis, coupled analysis, optimization, validation. Now, coming to FEM design case study 1. The study provides for optimal economical and technical solution obtained through successive improvement made in the design phase, obtained through the numerical modeling and the conquering the requirement of the product specification, and 3 dimensions numerical modeling of result for a hybrid stepper motor obtained using finite element method in the design stage is analyzed. And then the stator is made laminations of stacks of FESI, has 8 stator poles and 10 rotor T, and the stator is stacked 2 rotor semi armature and the 1 magnet. And as you can see in the figure how it look like typically in the figure for the with the dimensions like. So the rotor has a 1 magnet between the 2 semi armatures, and with the longitudinal magnetization, rotor has 3 parts: 2 semi armature with the 90-degree teeth each made of soft iron and PM, and the following materials are used like iron silicon lamination FESI for the stator, and magnet iron 416 for the rotor, and semi cobalt PM. Now for the computation of the design torque, the winding is not powered, thus the magnets are to be only magnetic field source. The FEM mesh quality is of particular concern in the numerical simulation, and gap thickness here 0.1 millimeter compared to the stator output diameter here is 86 millimeter, and the mesh must be adapted to match the required resolution in different motors and area in order to obtain the conclusive result. And here you can just see how it look magnetic field density variation values in Tesla with the colors shown in the variation of this flux density in Tesla. So the maximum value 1.7 in Tesla was found in the stator, and stator back iron has low flux density as compared to the stator pole teeth nearly half, and rotor has a flux density approximately 1 Tesla. So now the flux lines for the hybrid stepper motor is shown here, and sequence NS pole is developed for the motoring, and field lines for magnetic flux density value in Tesla are shown here in the figure. So now coming to detent torque is computed when the winding is not supplied and the PM are the only magnetic field source. The calculated detent torque has a maximum value of 7 millimeter Newton meter, as you can see in the diagram. So torque is with torque angle characteristic and consistent working condition. So now thus coming to conclusion of this, several factors such as air gap length and material influence strongly the hybrid stepper motor design outcome, and the magnetic flux density reaches the maximum value of 1.7 Tesla in the stator teeth. And since the hybrid stepper motor has a large number of teeth on the both on stator and rotor and a very small air gap, the magnetic saturation teeth becomes severe when the flux density in the air gap increases. Now coming to case of FEM design case study 2. So a simulation approach of equivalent circuit extraction for hybrid stepper motor based on electromagnetic finite element analysis analyzed. A reduced order model of the HSM is created for the purpose of system level analysis considering the integration of controller. So a 3D model of the hybrid stepper motor is constructed in ANSYS Maxwell, and there are 2 rotor cups with 50 teeth on the each cup and piece of permanent material in between the 2 rotor cup, which is axially magnetized, and each tooth on the rotor becomes a magnetic pole, which leads to a total of 100 poles and thus the 50 pole pair. And you can see this hybrid stepper motor FEA full model, then the rotor model, how it really look like typically with the winding and then the half model and the cross section width of half model. So there are 8 stator pole and 2 rotor and 2 phases. Accordingly, on the stator, each stator tooth, there are 5 small teeth corresponding to the 7.2 degree 360 by 50 degree rotor full pitch, and then step angle is theta is equal to 360 by 2 and 5 into NP, and putting the value it comes 1.8 degree. So theta is the step angle and psi is the number of rotor poles and NP is the number of phases, which give 1.8 degree of step angle. Now, when winding are excited, stator poles turns into electromagnet, and the hybrid rotor with the permanent rotate at the calculator step angle, and the hybrid stepper motor model specification are given where number of poles 100, number of slots 8, number of edge 2, step angle 1.8 degree, stator core dimensions 84 millimeter into 86 millimeter, 86 millimeter into 80 into 20, and coil turns 9, rated power 30 watt, and rated voltage 5 volt. To create the EC of SCM, the first step is to perform finite element analysis of hybrid stepper motor in Maxwell by sweeping the two-phase current with the range of interest, that is -10, -5, -1, 0, 1, 5 and 10, and sweeping rotor position with 10 increment and the full maximum rotating angle set of 7.2 degree mechanical degrees, full pitch between the two rotor teeth. And next, a lookup table will be generated automatically from the Maxwell containing all the results from FEA, including the flux linkage and torque information for each operating point, and the limits of the range of the current sweep should be chosen such that they exactly exceed any current the motor would experience in the operation of the system. So the more points defined within the current and the rotor position sweep, the more accurate EC result will be obtained. However, the simulation time of EC generation will be longer, and once the sweep angle complete, a model can be integrated into the ANSYS simpler for circuit modulation. And typically coming to this, the hybrid stepper motor EC model with the controller using ANSYS software. When here is the bridge controller for 2 edge bridge for the typically each phase, 1 edge bridge and for another edge bridge, and how with the excitation, the position and the typically voltage and current are there in the winding. So to validate the accuracy of the HESM EC, typical analysis of the HESM have been done in finite element for comparison, including the holding torque and back EMF calculation, and the results are compared with the EC result respectively. Holding torque is defined as the torque of withstanding the maximum force between the rotor and stator to maintain the equilibrium position and winding being excited. And typically the comparison of finite element and your EC holding torque, and comparison of the finite element and EC back EMF torque. And our result of holding torque and back EMF show the good agreement between finite element analysis and equivalent circuit analysis, extraction analysis. Here flux density field overlay plot for holding torque analysis and back EMF analysis. Now coming to numerical problems. Question 1, a stepper motor has a step angle of 2.5 degree. Calculate the number of steps required for shaft to make 25 revolutions. So given here beta equal to 2.5 degree, 1 revolution 360 degree, 25 revolution equal to 25 into 360 degree, and then n equal to TR upon beta, where n is the total number of steps, TR is the total revolution in degree. So n equal to 25 into 360 by 2.5 degree, that is 3600. Question 2, a two phase 2 pole PM stepper motor has n equal to 1200 turns per phase and is loaded with the external torque T shaft equal to 0.1 Newton meter. The motor is fed from with the rectangular waveform of the magnitude of current, which is I equal to IB equal to 1.5 ampere. Only one phase A or B is fed at a time. Find the peak magnetic flux phi F required to accelerate inertial torque load J equal to 1.5 into 10 power minus 4 kg meter square from speed eta in this sigma 1 to 50 to sigma 2 to 50 radian during the delta t equal to 0.08 second. So assumption the stator field reaction on the rotor field leakage flux and the damping rays are neglected. So now angular acceleration is d eta equal to dt equal to eta 2 minus eta 1 upon delta t, and putting the value it comes 2500 radian per second square. Electromagnetic torque required is T dynamic equal to J d omega upon dt plus d shaft, and putting value it comes to 0.4775 Newton meter. So first term is predominant and the torque developed by the stepping motor is mainly dependent on the dynamic torque required to accelerate the inertia of the rotor and other rotating masses. And the third, the magnetic flux linkage is Pt equal to 0, the step angle 2p equal to 2 and f1 equal to 2 and theta is equal to 90. It means that for a 4-stroke commutation, the necessary torque developed by the motor should be calculated as t equal to theta is equal to 90. Thus, the magnetic flux required is theta phi f equal to t sin divided by p nia sin theta sin p theta, and putting value it comes 2.64 into 10 power minus 4 Weber. And if, for example, the dimensions of PM are Wm equal to 25 millimeter and LM equal to 35 mm, and the leakage flux is negative, the air gap magnetic flux density should be B is equal to phi f upon Wm into Lm. So putting a value comes 0.3 Tesla. Now coming to question 3, the hybrid stepping motor has the rotor outside diameter T2 out equal to 51.9 millimeter, stator outer diameter T1 out equal to 92 millimeter, and the air gap is equal to 0.25 millimeter. The stator has 8 poles on each with the 5 teeth, and the rotor has a S2 equal to 50 teeth on the rotor. Each electromagnetic disc, calculate the ideal stator teeth per tooth pitch. Find the magnetic flux distribution using FEA for one rotor disc with the stator and rotor teeth aligned and with the teeth totally misaligned. Assume that there is no current in the stator wind. So now coming to rotor tooth pitch, the 50 teeth is T2 equal to 360 by 50, that is 7.2 degree, and the most suitable stator tooth pitch is defined as T1 equal to 7.2 degree divided by 180 degree minus 7.2 degree into 180, that is 7.5 degree, and 2D cross section FEM analysis of one pole of the motor is sufficient to show the flux distribution, and the stator teeth are rectangular to shape while the rotor teeth are trapezoidal. And you can see in the dimension how the magnetic field distribution of the stepper motor with the stator and rotor teeth aligned and the stator teeth misaligned. Now coming to question 4, a PM stepping micro motor 4-pole cylindrical rotor made of isotropic barium ferrite and has the outer diameter 1 millimeter, inner diameter 0.25 millimeter, and length of 0.5 millimeter. The stator winding consists of a single coil with N equal to 1000 turns made of copper conductor with its diameter D equal to 25 into 10 6 millimeter or 25 micrometer. The average length of the stator turn is 3.54 millimeter. The motor is fed from 3-volt rectangular pulses. The frequency of the input pulses is variable. However, 100 Hz has been assumed as the rated frequency. Find the magnetic flux distribution in the longitudinal section of the motor and the steady state synchronized torque as the function of the rotor position. Now coming as a solution, cross section area of the stator conductor is S equal to pi d square by 4, that is putting a value it comes 490.87 to 10 power minus 12 meter square. The stator winding resistance is 75 degrees Celsius, R 75 equal to 147.4 after putting value, and the magnitude of the current pulse is I equal to Im V upon R, that's 0.02 ampere, and the current density J equal to 0.02 divided by area, that comes 40.74 into 10 power 6 ampere per meter square. Or in order to electric micrometer, it is very high. So a 2D FEM model has been built. The magnetic flux distribution theta equal to 1 degree and I equal to 0.02 is plotted in figure I. Now the synchronizing torque is calculated using the Maxwell tensor line integral method, and the PM rotor is shifted in increment of 5 degree until a full electrical cycle is completed. The figure in next slide shows the reluctance torque of the unexcited motor and the total synchronized torque of the excited motor, which is the sum of the reluctance and the electromagnetic synchronous torque, and the zero rotor angle theta equal to 0 correspond to the q axis of the rotor aligned with the center axis of the vertical stator pole. And typically the synchronized torque and reluctance torque as a function of the rotor poles, as you can see here. I mean, these are the typically textbook or references which are referred in preparing this material, so you can refer that to go more in detail. And thank you.